Hi everyone, I am Asmar Nadeem. I'm the first author of this work, Contextual Multi-modal Alignment for Dynamic AVQA, aka CAD. This work has been done in CVSSP as part of AI for Me project, which is a prosperity partnership between CVSSP, University of Surrey, and BBC Research and Development. Now, this work mainly focuses on audiovisual question answering. Audiovisual question answering, or AVQA, involves using deep learning algorithms to analyze and respond to questions related to the video content. The video content may have audio and visual modality. This application enhances user engagement by providing interactive and dynamic experiences with the video content. Below, you see two examples from music AVQA and AVQA dataset. On the left, we have a example where the question is which clarinet makes the sound first. So if we have only a visual questioning answering model or VQA model, we will not be able to answer this question because we don't know the sound because there is no audio modality. Then if we have an audio question answering model or AQA model, then we cannot say which clarinet makes the sound because we cannot see the clarinet. We can only hear the sound. We only have the audio modality. Similarly, on the right side, we have an example from AVQA dataset. The question is, why did the stick fall in the video? So there are four options. But when we look into the visual frames, we don't see any train. What we see are trees, a stick falling, and maybe a road, a sign, and that's it. And maybe a red light. But when we look into the answers, the right answer is the C answer. Here comes the train. Now, if we have to come to this answer, we should have both visual and audio modality. We should be able to see the stick falling, and at the same time, we should hear the train whistle. Then these things together, stick, red traffic light, stick falling, and train whistle will help us in achieving the right answer. Now, what are the AVQA requirements? So in a AVQA scene, we have day-to-day complex scenes. We need to identify objects and actions, and then we need to capture the spatial information together with the temporal dynamics, as we can see in these examples. What is an AVQA objective? The objective is to generate answers using both audio and visual modalities in a way that it satisfies the question. The question is in the form of text. Here we see two state-of-the-art methods. One on the left is from He, Suing, Yun. In this method, they have used all the three modalities. They have used different kind of feature encoders for text, audio, and visual modality. And then they also introduced a pre-training task, which is basically masked language modeling for language, skewness for audio, and coordinate-based task for visual modality. And then they have question answering or grounding for multiple modalities. In this way, the architecture is basically an encoder which encodes all the modalities, fuses them, and then the decoder basically predicts the answer. Similarly, on the right hand side, we have a work from Guang Keo Lee. Here, they also have feature encoders for all the modalities. But what they do, instead of doing any kind of pre-training, they use spatial grounding and temporal grounding to achieve the right answer. Both of the methods are state of the art in AVQA domain. Now, what are the AVQA challenges? The main challenge that I can see is the imbalance between audiovisual and text information. For example, if we look at the figure below, we can see we have a word dog. But when we look at the visual information, it's not just dog. There is a floor, there is an occluded door of the room, and there is another dog. Similarly, in audio, we may have more sounds than just the sound of the dog. Now, what is this misalignment? So when we have this dog in the text, it's just one word, but the visual information is way more than that, and similarly the audio information. So we need to create a balance. Another thing is misalignment between audio and visual streams on spatial and temporal levels. If we see in the middle figure, we can see that there is a dog sound, and then in the visual frame, we can actually see a dog, but we need to spatially localize this dog. Similarly, we have a temporal misalignment between audio and visual streams. How? So when we look at the third figure, the most right figure, we can see there is a sound of dog, and it is directly like coupled with the visual stream. So when we hear the sound of the dog, we can actually see the dog. But we see in the last two frames, we look at the audio. So the audio has the dog sound, but the dog, when we see it is making the sound, is not aligned. So in this way, this temporal misalignment will hurt the performance. The next thing is inefficiency and complexity of existing AVQ methods. These methods largely rely on large-scale datasets, contrastive learning, and masking techniques. As we know, in contrastive learning, we don't have enough negative examples. If we don't have enough negative examples, we cannot learn. And on the other hand, these complex methods, they cannot solve the problem of imbalance between modalities and also the spatial and temporal misalignment. Now we look at the effects of these challenges, how these challenges affect the performance. So in the figure A, we have the performance or the results from state-of-the-art AVQ method. And what we see here, the first question here in the yellow class. Just to point out, the yellow class means that all the things which are part of one sample, the question, the audio, and the visual are one class. Similarly, green and brown are three modalities, but different from each other, but same in a green class, let's say, and same in a brown class. So the first question, what is the first instrument that comes in? The state-of-the-art method answers trumpet, which is red, basically means it's wrong. Let's have a look at the visual modality to explain this. In the visual modality, we see that there are two instruments. One is suona and the other one is trumpet. So what happens here, the model, when it looks at the visual frames, it sees the visual frames, but when it hears the sound of trumpet. It looks at the suona, but it hears trumpet, and because of the semantic imbalance, it favors the audio modality, and the answer is trumpet. But on the right hand side, which is our method, we see the right answer is SONA, because our method has aligned these modalities on spatial and temporal level. So when we see the SONA, we can actually hear the SONA. So our answer based on this is right. The second question, how many types of musical instruments appeared in the entire video? State of the art method says one. Now let's have a look at the visual modality of this question. So when we look at the first two frames, we see that there are two instruments in the room. One is piano, the other one is xylophone. But the next two frames show that the xylophone is being played, but not the piano. Similarly, the state-of-the-art method, it learns from the audio modality mode here, and it kind of ignores the semantics. So what has happened here, there is no semantic consistency because the question is about instruments appeared, not instruments played. So that's why the answer is true, which our method predicted rightly. What is our method? Our method is contextual multimodal alignment for dynamic AVQA aka CAD. In this method, we have three contributions, which basically solves the challenges or the problems we mentioned in the earlier slide. A parameter-free contextual block works on the visual features in a way that it does the learning on the spatial level, and it also reduces the imbalance with the semantics. On the other hand, we have a pre-training task based on multimodal fine temporal alignment that aligns the audio and visual streams temporally so that they don't have temporal inconsistency. The third thing is a chain of three cross-attention modules, which is a bit different than two conventional cross-attention modules in a way that it balances the information further from both audio and visual modalities with the question. Now, I'll explain the multimodal fine temporal alignment. What happens in this task, which is basically a pre-training task, we have a video containing both the visual and audio modality consisting of 60 seconds. So what we do, we divide this 60-second long sequence into 60 parts. So each part is 1 second long. And then we say we create cues of 1 second of audio and visual. And then we send this to the CAD architecture based on the sampling probability that we send 60% positive pairs and 40% negative pairs. So positive pair are audio and visual inputs belonging to the same queue. On the other hand, negative pairs are audio and visual inputs belonging to different queues. As we can see, we can easily control the number of positive and negative pairs. So this is a good pre-training task in a way that we don't have limited negative pairs. And then finally, we predict the audio time class label and also the visual time class label. So if they belong to the same class, as for T1, the label will be 1 and 1 for both audio and visual modality. And if they belong so the visual belong to the 2 class, T2, then the answer for visual will be 2, but audio belongs to T3, so the answer for audio will be 3. In this way, the method learns to temporally align the audio and visual streams. Now, what is our method in an end-to-end fashion? So we did the pre-training task. We got the model weights. From those model weights, we pass them to a contextual block, which I explained earlier. This contextual block only takes 80%, or sorry, 80% of the visual features as input. It does the mean on this input on the channel dimension, and then it creates some mask based on the threshold, and then it passes the mean or average features from the first step through a sigmoid, and then what it does, it randomly selects based on the probability of 90% from the mask or either from the contextual features, and then we multiply this random selection to the original visual features, and we get the final visual features, which we then pass through the cross attention blocks, and finally we get the classification label. What does this contextual block do other than adding to the performance? It reduces the pre-training time and training time because it compresses the visual modality. So uh, 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 so without contextual block, uh, if we you just train the state-of-the-art method, the pre-training hours are 205.7, but when we use the contextual block, then the training pre-training hours are 131. Similarly, the training hours reduced from 2.1 to 1.6. With our method, the pre-training hours reduced from 257 to 149. Similarly, for training from 2.4 to 1.7. Now, what is the cross attention mechanism? In the cross attention mechanism, one thing which we mentioned was the third cross attention block, which takes the query from the audio cross attention block as input, and then uses the visual modality from the output of contextual block as key and value. In this way, we process the information through these cross attention blocks. Now, our method improves on the state of the art. How much it improves? It improves around 9.4% on music AVQA. Specifically, it improves 10.7 on audio task, 7.7 on the visual task, and 5.5% on the audio task. Next is basically our testing on other data sets, which are basically activity net QA and MSR VTT QA. Our method improves on them as well. Qualitative results, in terms of qualitative results, you can see our method produces right results for all the three categories and different scenarios. For example, audiovisual temporal in the first scene, which I explained earlier, our method predicts Sona rightly. And then in the figure 2, we have a location-based question for visual scenario. So you can answer this question just based on the visual scenario. And then there are examples based on a comparative, and then visual location-based, visual counting-based, and audio counting-based. Now the ablation results. So without pre-training, our method has less performance, around 4% less, and then without contextual block, the performance is around 2.5% less. So if we only use 3 cross attention blocks and we don't use pre-training or contextual block, then we will have an improvement of around 2%. So if we use 2 cross attention blocks instead of 3 cross attention blocks, we will have a performance of 74.6%, and with 4 cross attention blocks, our performance is around 75.85%. Just to mention, these two contain the pre-training and contextual block as well. Next thing is basically adding the pre-training technique and the contextual block to the state-of-the-art method as a plug-and-play module, and we can see that there is a performance on the state-of-the-art method as well. And the next is basically using only the question query as input and not the audiovisual, and we get 60% performance. And if we mask the visual modality and use only audio Q and Q modality, then 68%. And if we don't use the audio modality and we only use the visual and question modality, then 71%. And if we use all the modalities and as input, so the performance will be 78. Uh, as I mentioned earlier, our method also achieves state-of-the-art performance on MSR, VTTQA, and ActivityNet QA, which you can see here. In conclusion, we have an old method for AVQA task, which features parameter-free spatial alignment and a pre-training task for temporal alignment, and then a cross-attention mechanism for semantic audiovisual modalities balance. It outperforms the state-of-the-art methods on AVQA. Applications can be extended to video captioning, speech, speaker recognition, and action recognition. In a way, it addresses the multi-modality misalignment challenges for unbiased decision making and enhanced accessibility. Thank you.